Hi everyone, welcome to another video by Cheenta. I am Rajteer, and in today's video, we will bring close the fundamental basics of this number theory series. In this video, we will talk about two slightly advanced but extremely important topics. One is the Chinese remainder theorem, and I'll talk about why it's such a good tool. The same goes for the topic of modular inverses. We've seen how numbers add, multiply, and subtract modulo some number. And I said that we later see how division works. You already seen a little bit of it in the cancellation rule in the last video. Today we'll see it properly in the form of modular inverses. We'll see that they behave really, really well. In fact, exactly the way we'd want them to be. And we'll see two problems. One is the 2005 IMO, the International Math Olympiad, P4. That will be our prototypical example of modular inverses. And we'll also look at an AIME problem, which will highlight the usage of the Chinese remainder theorem. I hope you enjoy it. And let's get into it. Right. So as before, the topic is inverses and CRT. And these are the two problems. Problem one is from the 2005 International Math Olympiad. That's the fourth problem. It says that determine all positive integers relatively prime to all terms of the infinite sequence 2 to the n plus 3 to the n plus 6 to the n minus 1 or n greater than or equals to 1. What this problem means is that you have the sequence, right? an, which is 2 plus 3 plus 6 minus 1, right? Which is 10, right? The next one is 2 square plus 3 square plus 6 square minus 1, and so on. We keep taking elements in the sequence, and the question is asking, you have this sequence of numbers. Can you find all positive integers which is co-prime to every single element in this sequence, right? So, for example, if I'm not saying that's what a sequence looks like, if our sequence was 10, 100, 1000, and so on, then an easy example of a number which is covariant to every element of the sequence is 3, right? 3 doesn't share any factors with 10, 100, 1000. So that's the kind of numbers we're looking for. Obviously, our sequence is not that simple. It's a complicated looking sequence. So can we find a number, or can we find all the numbers for which is co-prime to every single number in the sequence? As usual, pause the video and try the problem on your own. Right? The next problem is, for a positive integer p, define the positive integer n to be p safe if n differs in absolute value by more than 2 from all multiples of p. So hope that makes sense. For example, the set of 10 safe numbers is 3, 4, 5, 6, 7, 13, 14, and so on. So you can think of it as you have the multiples of, say, 10 in this case. So there's 0 is a multiple of 10. 10, 20, and we don't really look in the negative direction. And so we want all the numbers which are, a number is called 10 safe if it's not like this. So in an interval of length 2 around any multiple, you don't want to be there. So for example, 9 won't be 10 safe, 8 won't be 10 safe, 11 won't be 10 safe, 12 won't be 10 safe, which you can see doesn't work. Right? So we want to find the number of positive integers less than or equal to 10,000, which are simultaneously 7 safe, 11 safe, and 13 safe. Okay? We'll see that, so this is a hint if you want. This problem makes use of a very cheeky, and I'll get to it later, very, very nice use of modular inverses. And this is a classic example of a Chinese remainder theorem problem. And I'll also tell you how to spot a use of Chinese remainder theorem. It's actually surprisingly clear sometimes that we want to use the Chinese remainder theorem. So I'll talk about that as well. Right. So take a moment and try the problems on your own. And then later I'll show how to do this. Great. So the first thing I want to talk about is inverses. Okay. We already kind of seen the idea, right? In the cancellation rule, we saw that if AB was congruent to AC mod N, you could cancel off A if A and M were coprime. Right? And we kind of grouped together all of these guys together, which are coprime to M, and we called it the reduced residue system, right? And this system worked really well in a multiplicative setting. Having inverse is really just a natural next step. So I technically define what inverses are. So a modular inverse, so given integers a and integer a and modulus m, we say that x is the inverse of a mod m, where we understand that x is a residue. So it's a number between 0 and m minus 1, right? Is the inverse of a mod m. We say this if ax is congruent to 1 mod m. That's the definition. Why? The idea is that if ax was equal to 1, that's the same thing as saying that x is congruent to 1 by a mod m. That's the idea. And I mean, functionally, that is what an inverse is, right? Think about how inverses work over the rational numbers. If I ask you, what is the inverse of 2? You tell me half. But remember that half is a symbol being made up. I've spoken about this in a different video of mine, about what half is or what square root 2 is and stuff like that. We don't get a natural, inherent, intrinsic, if you want, inverse of 2 in the integers, right? There's no integer which when you multiply with 2, you get 1. That is what being an inverse means. An inverse is a number. If I ask what is the inverse of anything, a multiplicative inverse, it means give me a number which I can multiply with this number to get me 1. That does not naturally exist in the integers, so we make up new numbers and call them half and so on. The thing about working modular m is that modular m, you only have finitely many numbers, 0 up to m minus 1. This is a disadvantage and advantage at the same time, as we've seen over and over again. But in particular, a lot of the times you have inbuilt inverses. For example, let's take an example that's always illuminating. Let's look at 2 mod 5. Okay? And I can ask the question, what is the inverse of 2 mod 5? So let's look at all the options. That is the big advantage, working modular now. We have only finitely many choices to check from. So we can look at 2 into 0, 2 into 1, 2 into 2, 2 into 3, 2 into 4. And those are all the possibilities. So what is 2 into 0? 0 mod 5, 2 into 1, 2 mod 5, 2 into 2, 4 mod 5, 2 into 3, 6, which is 1 mod 5. So 2 into 3 is congruent to 1 mod 5. So 2 is the inverse of 3 and 3 is the inverse of 2, right? That's the good thing, that when you work modular number, you don't have to invent a symbol to talk about the thing that which you multiply with 2 to get 1. You don't have to make a new symbol for half. That number already exists in your system. That's a big advantage, right? So we can ask the natural question, when do inverses exist? I never said an inverse exists. I just told you what an inverse is. So when do inverses exist? The more specific question is, this is a heading if you will, more specific question is, given A mod M, when does 1 by A, or we write it in a nicer way as A inverse, so that we don't have to talk about actual fractions, modular, when does 1 by A exist? And the answer, as you may have come to expect by now, is if and only if A and M are coprime, right? You can find the 1 by of any number as long as it's coprime graph. And I mean, I can tell you very clearly why that is. Let's look at what happens if A is not covariant to M. So say A and M share some factor D, right? Say GCD A and M is equal to D, which is greater than 1, some non-trivial common factor. And say A had an inverse. So say AX was congruent to 1 mod M for some X. What does this mean? It means that AX is equal to 1 plus some multiple of M, MK, right? Bring this M over to this side. AX minus MK is equal to 1. You already might see it going on from Bezier type argumentation. So the point is that there's a factor of D sitting inside A and a factor of D sitting inside M. So D divides this entire left-hand side, but the right-hand side is 1. Can't happen. But this also kind of tells us how to find inverses using a different method. So, which is a contradiction. Now say A comma M is equal to 1. A and M are coprime. Right? This impossibility gives us an insight into how to find an inverse. So say A and M are coprime. By Bezier's theorem, which I have covered before, I can find integers x and y such that ax plus my is equal to 1. Look at this equation modular m. This x is exactly the inverse, right? Implies ax congruent to 1 mod m. Right? If I look at this equation mod m, the multiple of m obviously becomes 0, and ax is ax and 1 is 1. So ax is congruent to 1 mod m. So the x, the Bezier coefficient of a that you get when you look at a and m, that is the inverse of a. Right? So, and we know how to find Bezier coefficients using the Euclidean algorithm. So you can find inverses of numbers by running the Euclidean algorithm backwards. A quicker way is by appealing to results you've already seen, Euler's theorem. Euler's theorem implies that a into a to the pm minus 1 is congruent to 1 mod m, right? Because a times a to the pm minus 1 is a to the pm, this is congruent to 1 mod. That's another sometimes quick way of finding the inverse of a number. Think about what this means for a quick second. Think about what this means for the reduced residue system. S consisted of all the things coprime to m, up to m. What this tells us is that you can multiply, add, subtract, divide, do anything in this set and end up inside the set, right? I can take some number here, a inside the set, and talk about 1 by 8. It's still inside the set. I can multiply 2 numbers inside the set and I'll still get a number inside the set, right? Obviously, everything mod m. Right, so this is a very nice example of something that's called a field, but it's a quick trivia for you, but this has very far-reaching applications. And in particular, it also gives us a way of thinking about the Chinese remainder theorem in a more general light once you learn about ring theory, but that's beyond the scope of these lectures. Right, so we know what inverses are. How do they work? They work exactly how we want them to. I'll give a few properties, all of which are proofs of this idea that inverses behave like fractions. Exactly like fractions. In particular, if I take the inverse of A and I multiply it with the inverse of B, as expected, I'll get the inverse of AB mod M. Given that A and B are both invertible. So obviously A and B are coprime. A and B are coprime to M. That's granted. Remember that this also implies that AB is coprime to M. So AB inverse exists and it equals 1 by A times 1 by B. So this is kind of just saying the simple fact that 1 by A times 1 by B is equal to 1 by AB. They add the way we want them to. In particular, A inverse, so A times B inverse plus C times D inverse is congruent to congruent to AD plus BC times B inverse D inverse. Mod M, of course. You might say, okay, that's awkward. Why should this be true? Because it mimics the fact that A by B plus C by D is equal to AD plus C by B. To formally verify this stuff, I leave that as an exercise to you. But the point is, inverses behave exactly like fractions. And this kind of immediately solves this really supposedly hard problem for us. IMO 2005 P4. The main observation that you have to make is that for any prime, so I'll write this problem down. We want to really just find what primes show up in this sequence, right? That's like a subtask that encompasses a large part of the problem. You're asked to find all the numbers which are co-prime to this elements of this sequence. So you could ask what primes show up in it. If I find all the primes that show up in it, I could at least think about what primes don't show up, and hence all the numbers which will be relatively prime to it. But the point is that if there's an even number, which we know is already true, if 2 shows up as a prime in this sequence somewhere, right, in that some number is divisible by 2, we know that no even number will work for us. What I'm trying to say is, if the sequence is 5, 7, and 10 somewhere, which we know already happens, the point is that no even number will be able to be co-prime to every element of the sequence because it will share the prime factor with 10. We just really want to know what primes show up, right? The main observation is that, well, of course, we want to only put n as a positive integer, but if we are as bold as setting n is equal to -1, then half plus 1 by 3 plus 1 by 6 minus 1 is equal to 0, right? Half plus 1 by 3 is 1 by 6 is 5 by 6. 5 by 6 plus 1 by 6 is 1. 1 minus 1 is 0. Obviously, this is informal. We can formalize this, right? We know that work modulo a prime p for any p greater than 3. Then 2 to the p minus 2 plus 3 to the p minus 2 plus 6 to the p minus 2 is what? Half plus 1 by 3 plus 1 by 6, and if I go minus 1, hence 0 mod p. So any prime greater than 3 divides some member of the sequence. So the only thing, and obviously we know that p is equal to 2 also divides the member of the sequence. The very first one, it divides 10. So every prime shows up in this sequence at some point. There's a number which is divisible by 2, there's a number which is divisible by 3, 5, 7, and so on. So no number can be relatively prime to every member of the sequence because it do share a prime factor with some member. Slightly subtle, but I hope you see the point. Hence, the only number which works is 1. So that was very cheeky, and I remember when I was trying to solve this problem and I spent a long time, and when I saw that the trick was half plus 1 by 3 plus 1 by 6, it was infuriating, but also very enlightening because inverses suddenly clicked for it. So I think this is a great example. So I hope you see the point I'm trying to make. Inverses work kind of exactly like fractions. And you can formalize it further if you try to use the language of fields, which I will not do. For now, take this as a thing that definitely works. Right. So that's that for inverses. The next thing I want to talk about is the Chinese remainder theorem. You've already kind of seen it. Look at an AP, right? Look at all the look at this sequence. 3, 8, 13, 18, 23, 28, and so on. We can write this very simply. These are all the numbers which are congruent to 3 mod 5. Right? They're of the form 5k plus 3. Well, numbers 3 mod 5 more than 1. We look at positive integers which are 3 mod 5. I can ask the very natural question, for example, Do any multiples of 4 show up? We see that they do, right? 28. Do any multiples of 6 show up? 7, 9. So we're really asking, is there a solution to this simultaneous system of equations, x congruent to 3 mod 5, x congruent to 0 mod, whatever it is you like, 7, say. How do you solve a system like this? We already saw last time. You just move stuff around. So generally, let me try to solve this problem. Say I want to solve x congruent to a mod m, say a1 mod m1, and x congruent to a2 mod m2. We have to hold a slight caveat, which is that m1 and m2 are coprime. There's a version which we'll not get into, which involves a non-coprime moduli, but you have to really tussle with the equation. Right, so how do I solve something like this? What do numbers which are of the form a1 mod m1 look like? They look like a1 plus m1 k for some k. The idea is to plug this number into this equation and find out something about k. Right? Plug it in. And a1 plus m1k congruent to a2 mod m2. Hence, m1k is congruent to a2 minus a1 mod m2. This is where our learning of inverses will come in handy. This k is coupled with this m1. I want to take it out. It would be great if I could divide by m1, right, on both sides. I can, because m1 and m2 are coprime. So I can talk about 1 by m1, and here I can cancel it. So k is congruent to a2 minus a1 times m1 inverse, which I know exists, mod m2. This number. Right? This is some number, right? If I call it a. See? Some proper residue mod m2. So k is congruent to a mod m2. Which I can write succinctly as k is equal to a plus n2l for some integer l. Plug that back in. This is a1 plus n1 into a plus n2 into l, which is what? It's a1 plus m1a plus m1 m2l. Note that a is some fixed number, right? L is the one that's allowed to vary. Initially, k was the one that was allowed to vary. It's kind of like a dependence of parameters. K was the one that we were moving around. We could have k to be anything, but then k got a dependency based on the second congruence, right? Then the dependence shifted to L. So L is our free variable of sorts. So A is some fixed number. It's 2, 5, whatever. So this is a fixed number that we can calculate in an example. So in fact, what this tells us is that there's some unique number modulo m1, m2, right? This tells me that x is congruent to something, this number, mod m1, m2. So let's do an example. X congruent to say 2 mod 3 and x congruent to say 3 mod 4. Okay. I want to solve this. So I want 3k plus 2 congruent to 3 mod 4, and which implies 3k is congruent to 1 mod 4. This is actually just asking what is the inverse of 3 mod 4, which implies that k is congruent to 3 mod 4. Remember, so this is another thing about inverses, they work exactly as you expect. 3 is minus 1 mod 4, right? Minus 1 into minus 1 is 1. Minus 1 is its own inverse. That's the idea. So, yeah, 3 is its own inverse, mod 4. 3 into 3 is 9. 9 is congruent to 1 mod 4. Our verification. So, k is congruent to 3 mod 4. Hence, x, which was 3k plus 2, is actually, this implies that k is of the form 4l plus 3. I'll plug in that 3 into 4l plus 3 plus 2, which is 12l plus 11. Right? which implies that x is congruent to 11 not 12. There's also a backwards compatibility here, if you will. If x is congruent to 11 not 12, it also means that x is congruent to 11 not any factor of 12, right? 3 and 4 at the same time. Right? What is 11 mod 3? 2. What is 11 mod 4? 3. Now go back. This is what we were looking for. So it's kind of like lifting to a higher modulus, where whatever 2 mod 3 means and whatever 3 mod 4 means, they become the same statement. How that makes sense. The Chinese remainder theorem is a very delicate construction tool, and it's also a proving tool. It's many things. There's this lovely note that Evan Chen has, which really gets into the detail of this. So he talks about the CRT as a Chinese remainder theorem as a tool that can be used in 3 different ways: construction, lifting, and destruction. And there are great ways of thinking about the Chinese remainder theorem. So I would certainly urge you to look at that. It's freely available on the internet. Please take a look. That's the idea. And this idea can be wholly written as working modulo M1, M2, where M1 and M2 are co-prime, is the same thing as working modulo M1 and working modulo M2 simultaneously. You might notice that I haven't really written down the exact version of Chinese remainder theorem yet, which I will do now. And what we've done for 2 equations here, you can imagine that I could do for 3 or 4 equations by just doing it in order. If I had 3 equations I wanted to solve, I'd solve the first 2 and then solve the next 2. More generally, if I had given pairwise coprime numbers, this is Chinese remainder theorem. Coprime numbers M1, N2, Mk, as you will. What does pairwise coprime mean? Any 2 numbers are coprime. So 2, 3, 5, for example, are pairwise coprime. And the equations x congruent to A1 mod M1, x congruent to A2 mod M2, x congruent to AK mod Mk. What does the CRT say? There exists a unique solution. That's important. Modulo M1, M2, Mk. All the numbers that satisfy each of these equations at the same time fall into one modulo class, modulo all of the one modulo class, modulo M1, M2, Mk. So if I had, x congruent to A mod 2, B mod 3, C mod 5, every number that satisfies all of these simultaneously is some specific number, some D mod 30. I hope that the point that I'm trying to make is clear. Every number, every solution that satisfies this is congruent to some fixed number modulo 30. And yeah, the idea is that sometimes you want to solve an equation mod, say 28. Solving that equation is the same thing as solving the corresponding equation modulo 4 and modulo 7. Right? If I wanted to find out if something like find all numbers which are congruent to n squared plus n plus 1, find all numbers n such that this is divisible by 6. You would do this the same thing as, so 6 divides this number. This is a bit weaker than the Chinese remainder theorem, but the philosophy is the same. 6 divides this number if and only if 2 divides it and 3 divides it. This is much weaker than the Chinese remainder theorem, but the idea is that working modulo a product of coprime numbers, same thing is working modulo the individual factors. let's see how this solves our AIME problem. The idea is that since 7, 11, and 13 are coprime and we want to satisfy a certain modulo condition, right? We really just don't want. What does it mean to be P safe? It means you are not congruent to 0, 1, or 2 mod P, right? We just look at the problem. Neither are you congruent to P minus 1 and P minus 2. You can't be congruent to these 5 numbers modulo P if you want to be P safe. And hence, you can be congruent to P minus 5 number modulo P. So you want to be 7 safe, you can be some 2 unique residues mod 7, right? So, which would be, I think, 3 and 4 mod 7. Those are safe. Similarly, if you want to be 11 safe, you would have 6 moduli residues that you are okay with. And similarly for 13, you have 8, right? P minus 5. So all the numbers which are simultaneously 7, 11, and 13 safe have 2 into 6 into 8. They have these many choices, modulo 7 into 11 into 13. And so there's a unique number. I'll know you just do a small calculation. This is, in my understanding, this is, I think, 1001, 7 into 11 into 13. So you have these many safe choices. I think this is 96. So 96 residues mod 1001 are safe, which means 960 numbers up to 10,010 are safe. So now you just have to check whether the numbers between 10,001 and 10,010, which ones are, not P safe. There are only 2. So it's 960 minus 2, which is 958. So this was really just an illustrative problem. I've actually imparted the idea to you already. Try this problem properly as homework, if you will. But the idea is just that a number is simultaneously 7 safe, 11 safe, and 13 safe if it is 1001 safe. Those 2 statements are equivalent. So yeah, this has been a slightly long video, I understand. But in some ways, we've gone over all the fundamentals of number theory, basic Olympiad number theory. There are lots of topics that come after this. We might take a look at them in the next videos, but we've really gone over the basics. And I hope you can start solving some problems now. I hope you enjoyed this video. Thank you very much for watching. Bye-bye.